math final project, we were assigned a problem in which we had to find the rate of change of temperature when given specific pressure. To do this, we use what we have learned throughout the semester, and we will also display this graphically as well. This problem talks about how temperature changes based on the water boiling at certain pressure. The temperature is measured in Fahrenheit, while the pressure is measured in pounds per square inch.
When the water boils, we can see that the pressure increases, so the temperature will increase as well.
We were provided also with an equation that approximates the data shown in the table. This graph represents the model in which, as pressure increases on the x-axis, temperature as well increases. However, the logarithmic function increases until a certain point where it stabilizes.
In point B, we were asked to find the rate of change of the equation of the temperature with respect to the pressures provided, which are 10 and 70. But first, to do that, we need to find the derivative of the equation of temperature, and after that, we can substitute the provided amounts of pressures in the equation that we already differentiated. So first, we're going to find the derivative of this equation of temperature. So the first thing we need to do is we need to rewrite the equation so we can eliminate the square root. So we're going to rewrite it with, and this part will stay the same because we don't need to change anything. And in here, we're going to put p to the 1/2 so we can differentiate it in an easier way. So now that we rewrote the equation, now we can find its derivative, and in order to do so, we need to use these rules. So in here, we can see that it is a constant, and when you have a constant, it will be equal to 0. So we only write 0 plus, and in this term, which is of natural logarithmic functions, the rule is to do u prime over u. So we're going to rewrite this number, and then the u, we find its prime, so it's times 1 and over u, which is p. And then in this term, we have x to the n. And the rule is to do n times x to the n minus 1. So in here, our n is 1/2. So we're going to multiply 1/2 times this number, which is 7.91, to the p 1/2 minus 1. Now we're going to simplify the equation. So this will be 34.96 over p plus, and in here we're going to multiply 1/2 times 7.91, which is 3.955, and then p, and here we're going to subtract 1/2 minus 1, so it will be negative 1/2. And now the final step is to bring down this negative 1/2 and make it a square root. So we rewrite this term, and now we're going to bring down the p with a square root.
Now that we found the derivative, to know what's the temperature when the pressure is 10, we're gonna plug in 10. So we have to do the derivative of temperature when pressure is 10. And we're gonna write 34 0.96 over 10 plus 2.155 over square root of 10. So this is the next step. We change the square root of 10 into decimals. Now we divide, and this is what we get. So now we add, and our answer would be 66. Right here. So now we know that when our pressure is 10, our temperature would be 4.7466 Fahrenheit pounds per square inch.
Here we can see the derivative from the original function. And now we're going to find the rate of change when pressure is 70. So now we're going to substitute in the derivative formula. And 34.96 will be over 70 plus 3.955 over the square root of 70. Now we're going to change the square root into a decimal. So now we're going to divide both terms in order to get a simplified answer. So now we're going to add both terms in order to get the final answer. Its units will be Fahrenheit over pounds per square inch. So here we can see that the rate of change when pressure is 70 will be 0.97240.
This graph represents the derivative of the model, and it shows that in y and x-axis the asymptote is 0. It also shows that the limits on both x and y-axis are infinite.
This graph shows the derivative function, and it can be seen that as pressure increases, temperature decreases, as for example when the rate of change in pressure is 10, the temperature is around 4, but however when pressure is 70 and the rate of change, temperature is less than 1, so it shows that it is decreasing. The graph in here shows the original model shown in yellow and also its derivative in pink.
We can see that the original function increases dramatically at first, but later on it gets to a point where even though the pressure still increases, the temperature doesn't increase as much as it did in the beginning.